So when we talked on Wednesday, we talked about product elimination, and we talked about how to like approach elimination problems, and we talked about finding the leaving group and then finding the alpha hydrogens because that's where the reaction is going to take place. And we also talked about the geometry, the anti-periplanar geometry and all that. So what we're going to do now is go through this E2 example, and then we're going to go through one of the E1 examples, and then we're going to work through some problems dealing with both types of reaction. So let me erase some of this so I can make some room. And then we'll make reference to the factors that we talked about, excuse me, that we talked about up top. We'll make reference to that while we're walking through. So the first thing you want to do is notice that there's a strong base present. And I think in one of the videos I sent, I gave you a list of bases. KOH is one of my stronger bases. Any amine base is also going to be a strong base. When you see that, that's kind of it's a clue towards the fact that it's an E2 elimination. All right. So the way this works, let's talk about the mechanism right quick. So I find my leaving group, which I have here. And then next to that leaving group, I got two carbons. I got a carbon here. Sorry. Carbon here and a carbon here. Those are the two carbons where elimination is going to happen. And it happens when you pull off the protons on those carbons. All right. So you have protons on either side, and those protons are going to be removed by that. That's the purpose of the base. So let's say the base. Let's do the left side. So my base is here. Right. So it's the hydroxide part of the base that's important. So my base is here. It's going to come in, give a pair of electrons to that hydrogen, and then at the same time, this is kind of just like the SN2. At the same time that you pull that proton off, you're also going to use that pair of electrons in the CH bond to make a double bond right there. That's one of the key characteristics of elimination is the formation of a pi bond. All right, so you're going to put that pair of electrons there, and you're going to lose the leaving group all at the same time. All right, so let me show you. Let's look on the other side of the arrow, see what we get. So we're going to get this for sure. All right, that's the conjugate acid of the base. And then we're going to get Ki. Because when the leaving group leaves and the positively charged potassium that's right here is going to end up with the leaving group. So Ki, and then my products, one of my products is going to look like this. Like that. There's a lag. Somehow there's a lag with my Wi-Fi, so I apologize for that. All right. Let me fix that. That doesn't look too neat. All right. So that's the first elimination product. And then the fact that you have two alpha positions right? Remember, this is alpha, and then this side is alpha to wherever the leaving group is. The fact that you have two alpha positions means that I can do that elimination on the other side too. So let me zoom in a little. Right, so I can do the same thing here. Boom. But this time the double bond is going to be on this side. Right, and again, it's all simultaneous. The base is doing proton transfer. At the same time, the CH bond is being used to make that uh, double bond, and you're losing the leaving group all at the same time. All right, so it's concerted, just like the SN2. All right, and then so that's one product, and then the other product is going to look like this. Like that. And then, of course, you'll get another water and another molecule of Ki. So if you want to put a 2 out here, that's fine. All right. Any questions about that? About the mechanism, about anything? All right. So let's talk about the fact that E2 favors tertiary carbons and it follows Zaitsel's rule because those two things are connected. Right. So of the two carbons here in the starting material, right, this one is on this side, it's tertiary. And then on this side, it's secondary. What that means is that when I make my products, where that secondary carbon is, I'm going to get the alkene that I make here is going to be what we call disubstituted. Right? And on the tertiary carbon, the alkene that I make here is going to be what we call trisubstituted. Right? What that refers to is the number of groups or the number of carbons that's attached to your double bond. So if you look here, right, you got a carbon here, a carbon group here, and a carbon group here on this double bond. So that means it's tri-substituted. Up top, you got a carbon here and a carbon here. So that means it's disubstituted. So it's two groups attached. All right. But for alkenes, the more groups you have attached, the more stable the alkene is. I'm gonna write it out. Right. So more substituted alkenes are more stable. So based on Zaitsel's rule, the major product is going to be the more stable product or the more substituted product. I think we went over that Wednesday, but I'll write it again. So Zaitsel's rule says your major for an elimination, your major product is going to be the more substituted product. Let me erase this. All right, so the major product is more substituted. That's what Zaitsel's rule predicts or indicates. Right, so when you do an E2 elimination or E1 elimination, it doesn't matter. It could be E2 or E1. When you do an elimination, the major product, according to Zaitsel's rule, is the product is the alkene that's more substituted. All right. Any questions about that? About anything? Let me know if I'm going too fast too, because we can slow down.
But you would still have both products in the end result?
Absolutely. Absolutely.
Okay.
You still make two products, but again, the product distribution is gonna what's what we're talking about now. So it may be 80-20, it may be 65-35. You understand what I'm saying? Maybe 70-30. It just depends.
Yeah, I got you.
Remember we talked about that term product distribution uh, when we talked about doing reactions on pre-existing chiral centers. We talked about product distribution. All right. Any questions about that? I think we should do some examples and then come back to the E1. Because the E1 is not that. It's almost, it follows the same path as SN1, except for when you get to the intermediate, you do an elimination as opposed to a substitution. Uh, and then I did talk about the geometry of the E2, right? Where you have to have what's called anti-periplanar geometry for the elimination to happen. And all that means is that the alpha hydrogen and the leaving group have to be on opposite sides of the same plane. All right, let's do a couple of examples. Then we're gonna come back up to E1. You got a bunch of examples down here that we can work through. Get all those. Okay, great. Here we go right here. So let's take, we're gonna work through A and, oh, C. C is a good one. A and C. Let's work through those. And F, A, C, and F. Let me do this first. Learn from my mistakes. Add a page right quick so we can have some room to work. All right, so we do an A, C, and F. Let's start with A because it's a fairly simple and fairly straightforward. All right, so what I need to do here is at first locate my leaving group, and then the hydrogens that are adjacent to that carbon containing the leaving group, that's what my elimination is going to happen. So this is right. All right. So when it says predict the products, we really don't have to go through the mechanism, but I'm gonna show you. I like doing it because it's good practice, right? So here's my base. Here's my base right here. That's a what we call a Tert Butoxide. It's a really strong uh, alkoxide base. Let me show you what it looks like. So the Tert Butoxide is looks like this, right? So that it's a tert butyl alkoxide. So you have an oxygen attached to a tert butyl group. If I can get this last methyl group right, I'll be all right. Right, so that's a really strong base. Sometimes you'll see it written with potassium and see it written out as KO T-butyl like that, potassium tert butoxide. I know for a fact that's in that elimination video that I sent. This is one of your more common bases and it's really strong. So whenever you see that, you know for a fact that you're doing elimination and not substitution. Right? So what happens in this case, let's do this side. This is coming here, boom, and then boom, you're losing chlorine. All right, so you're gonna get two products because you have two positions that can be deprotonated here as well as here. All right, so that first product is gonna look like this. Anybody disagree with that? And then for the other product, it's gonna look like this, right? I'm just gonna change colors of my arrows. So I'm coming here, boom, boom, and then boom, losing chlorine, right? Both sides are susceptible to deprotonation, right? So that's why you're gonna get two products. I'm gonna write that one in. So that's my second product. Question is, which one is major and which one is minor? What do you think?
Second one is probably the major.
I agree. Right? You see how your double bond here is di-substituted? All right, so you have a di-substituted alkene here. And then in the first product, you have a mono-substituted alkene. Right? That double bond only has one carbon attached to it. Right here. Everything else is hydrogen. Okay. Any questions about that? No questions. All right, let's do the next one. Go back up here. Let's do F, because C is a little tricky, so I want to hold off on doing C. Let's do F. So F is actually a 5-member ring. Bromine is my leaving group. All right, and let's see what the base is for that. It's just OH minus. Normally, you'll see that as KOH or sodium hydroxide. Right. The weird thing about the hydroxyl anion or the hydroxide anion is that sometimes you'll see it in a problem for substitution or an elimination. It can actually do both, but I'll make sure to on an exam to give you a base where you know immediately, oh, this is a base, this is not a nucleophile, right? But sometimes you'll see that OH proton written as a nucleophile as well. All right. So let's see what happens. Where are my alpha protons? Help me, somebody help me out. And how do you know how to locate them?
They're the hydrogens on the two carbons connected to the carbon connected to the bromine.
Okay, so the way you locate them is find your leaving group and then find the carbons next door, right? It's always going to be those hydrogens that get pulled off, right? All right, so now let's just go through the arrows because I think that helps a lot. Boom, 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 just like that. It's all concerted, just like the SN2, except you're not doing substitution, you're doing elimination. So what is that product going to look like? Don't now speak out at once. Now I know it's Friday. Is that right?
Yep.
Mm-hmm. And then same thing. Let's change. Let me switch colors so you'll see. So I'm coming here. Boom, boom, and then like that. It's the same mechanism on either side. It happens the exact same way. It's just a product that's different. All right. So this is plus this, and then now my double bond is down here. Boom. Here, and then there. All right. So the question here is, which one is major? What do you think? And tell me, why is major? Uh-oh.
The one on top because it has the three subgroups.
It's tri-substituted.
Yeah, that.
Yep. Sorry about that. Hit the wrong button. All right. You're right. It's this one. All right, so that's major and that's minor, based on Zaitsel's rule. All right. So the last one is a little tricky because it actually has, you're actually going to make 3 products. Let me draw that out. Should add another page here. Hold up. Let's see how many carbs that is. Just want to make sure I draw it correctly. So here's my leaving group, iodine, and then here's a CH3 group. So let's locate the alpha protons or the alpha hydrogens. You definitely know that. So here's my leaving group. So any carbon that's on the carbon adjacent to where the leaving group is going to be considered an alpha position, right? So here, and then here, because that's adjacent to the carbon where the leaving group is. Let me make that a different color. So that's the carbon where my leaving group is, right? So you have those 2 positions, and you have this carbon right here. Even though it's the way it looks kind of weird how it's drawn, but that's still alpha. All right, so that means that I'm going to get 3 products. Everybody okay? Keeping up? Let me see how many people we got now. Okay, we got 22. Still got a bunch of people that's not here, but that's okay. We just have to roll with who we got. I didn't even ask about the hurricane. How is anybody here that was affected? Anybody in the area, like on the Gulf Coast, Mobile, Pensacola, somewhere in Louisiana, anywhere like that?
Nah.
All right, that's good. We got hit here in Prattville. That thing came right up 65. Tore some stuff up in Montgomery too. But by the time the morning came, everything was good. Well, it was still cloudy, but it was no damage, not here. So, but all my mom and all my sisters are all in Mobile, so, but they straight. There's probably another one coming too, because we just in the middle of hurricane season. We ain't even through it yet. All right, so we're going to get 3 products. Somebody tell me what the if I start here. And then let's say if I start on this side, what's that product going to look like? Feel free to annotate if you can, if you're able.
Oh, snap.
That's all right. Just take your time. Okay. I'm with you. I see what you're doing. Okay. We need a methyl group. Yeah, right. Yeah, good. Okay. Let me see if I can. So you have here. Is that right?
Yeah, like that.
Mm-hmm. Okay, I agree with that. That's one of your products. What's the base? I didn't write the base down. It's just OH minus. We're gonna say KOH.
And then Ki.
Mm-hmm. So that plus water and Ki, right?
Would that methyl group next to the hydrogen that you just took away go away too?
No.
That you made a double bond?
No, the methyl group stays put. All I'm doing, I'm just kicking off the leaving group.
I'm talking about the methyl group next to the pi bond you just made.
Oh, yeah, my bad. I just didn't draw it in. My fault. You mean this one?
Yes.
Yeah, that's my bad. All right. So that's that. Boom, boom. All right. What about my next product? If I do this side, what do I get from that? Somebody want to draw that one in? Okay. 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 Good.
Is that right?
Yeah. Is that squiggly line? Is that the other methyl group?
Yeah, that's a methyl.
Okay. All right. I just want to make sure that that's right. That's good. So you're here instead of now your double bond is on the other side over here, right? Good.
Mm-hmm.
Yeah. Good. All right. And then the third product is going to take a hydrogen from up here. gonna take one of those. But for that, that second product, the OH came here, boom, boom, and then you lost your leaving group. And keep in mind, it's all concerted. So the rate law, when you write the rate law, is K times the substrate, and then times the base concentration. So the rate law is almost the same as the SN2, except for instead of your nucleophile concentration, it's the base. But it's a two-term rate law. It's second order overall, and anything you do to one reactant, it's going to affect the rate, right? So the same principles. If I double both, it's going to quadruple. If I triple both, it'll increase by 9 times. If I cut one in half and double one, it's no change. So it's the same principles that govern the SN2. The only difference is the outcome of the reaction, right? All right, what about the last product? If I take that, one of those hydrogens, what's the last product gonna look like? Sorry. Anybody? I gave you a head start because that one is a little tricky.
There'll be a pi bond to the right of the methyl group.
Right here. Yeah. Yep. I see what you did. That's exactly right. And then I'm gonna go ahead and write out that as a CH2. Right? So those are my 3 products. And that one comes from, let me go up here right quick and write these out. So the base is gonna come here. Boom, pull that off, boom, and then like so, lose your leaving group. Same mechanism, same arrows, different location. All right. Which one is major? What do you think?
The last one is major.
This one right here. That double bond only has 2 carbon substituents on it. Look at the one on top. Boom, 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 boom. You got 4 carbon substituents on that.
You look at the carbon after you make the products.
Yes, what we're looking at is so here's my double bond. I'm looking at what's bonded to it. I got 4 carbons bonded to that double bond. So this double bond is tetra substituted. Right? If you look at the one underneath it, it's tri-substituted. 1, 2, 3 things attached to it. And then this one is di-substituted. So the more substituted double bond is going to be the major product according to Zatzel's rule. All right, we're okay with that. Any questions about the E2? All right. So I wanna talk about. Yeah, I got time. I want to talk about the E1. We'll work a couple of E1 examples. And then on Monday, we're going to start conjugation. So I'm going to send you a video over the weekend to watch for that. So the next exam is going to be substitution and then conjugation. Those two topics, which will be next Friday. And it'll be hosted on, we won't start taking those ProctorU exams until after this next one. Because I'm going to go ahead and start scheduling those dates. And I'll send you the information for how to schedule and all that stuff. It's pretty easy. You just have to have a webcam. All right. Let's go back up here and start talking about the E1. And then we're going to work through, I want you to work through 861. Let's do D.
Dr. Russell,
Yes, A.
when we start using ProctorU, will the exam still be open note?
It depends. It depends on what the topic is.
Okay.
It depends on what the topic is. Sometimes when I set it up, I'll put a note in to whoever the proctor is that you can have one page of notes or you can have flashcards or something like that. But I'll let you know all of that beforehand.
Okay.
Yep. All right. So I want you to work through on your own 861 A and D. And let me put the date in here. Let me go back down to here. All right, let's go back up and look at the E1, and then we're gonna come back and work 2 E1 examples, so I can show you one of the characteristics of the E1. All right, so let's go back up to here. All right, so for the E1, it's a little bit different. It kind of follows the same path as the SN1 in that the first step is the loss of the leaving group. One of the classic E1 eliminations is the dehydration of alcohol. So we're going to look at that. So I'm going to erase, no, I can't erase that. I'm just going to pluck this out. Because I don't want to erase those notes, and I don't want to try to squeeze stuff in. But you can see here, I mean, I can't erase this part, right? That tertiary or secondary carbons will work. Also, protic solvents, right? Because those protic solvents do facilitate elimination if you have a hydroxyl group as your leaving group. The whole idea behind carbocation stability still remains because it follows the same path as SN1. And then it also follows Zaitse's rule. So let's put I got a page. Praise the Lord. We throw this in right here. All right, so this is, now we're talking about E1 elimination. So I'm gonna go through the mechanism. Actually, I'm gonna draw the product. So this is the product for this reaction. All right. So that's the product. The sulfuric acid is like a catalyst, right? You're always gonna regenerate that. You're never gonna it's not ever gonna be used up, right? If you remember when we made aspirin in Organic 1 lab last semester, one of the things we did was added 6 to 8 drops of sulfuric acid, even though it wasn't an elimination, right? That acted as a catalyst. It's a supplier of protons, right? Let me write that right here. A very good supplier of protons at that. So let's see what happens. So this mechanism, what do you remember about OH as a leaving group? Remember when we talked about converting alcohols into alkyl halides? What do you know about OH as a leaving group? Is it good or bad? I'll try to do that. It's a really poor leaving group. So in order to make it leave, we got to do something to it, right? We got to make it a better leaving group. So that's the purpose of the sulfuric acid in this case. It's going to protonate that alcohol and make it into water, convert it to water, right? Or hydronium ion. So let me draw out sulfuric acid, so you'll see exactly what it looks like. So it's this. And I'm gonna keep this structure up here too because it's important. It's very important to the overall mechanism. So this proton is going to get plucked off. So that first step is going to be a proton transfer. All right. So now we're going to end up here. That has a pair of electrons, positive charge. And then that's my intermediate. And then lurking is the conjugate base of sulfuric acid, which is this. Right, keep that in mind. Right, so now what do you think happens next? So I've made my OH, my hydroxyl group, a better leaving group. Now what do you think happens next? Keep in mind, go ahead.
I said water leaves.
It's going to leave, right? That's my leaving group. And so that's the rate determining step. Just like for the SN1, the rate determining step is loss of leaving group. For the E1, this is also the rate determining step. So now I get a carbocation intermediate. So that's my rate determining step. All right, now here's the elimination part. Right? It's the same idea when you're eliminating, right? The carbons that are adjacent to where your leaving group is, those are the carbons that give up a proton. Right? The question is, so I'm going to put down here H2O. The question is, what does the proton transfer to cause the elimination, right? Water can do it, or the conjugate base can do it. So that's a very important point to make about this E1. But there is no base present, no external base. So you won't add in a base to do E1. You don't need a base. So I'm gonna say conjugate. So the conjugate base or water can facilitate the elimination. All Right? So it can be the conjugate base of the sulfuric acid or the water. Personally, I like using the conjugate base because I won't have to have another step in the mechanism where the conjugate base pulls off a proton from H3O plus, right? So I'm gonna use the conjugate base. But keep in mind, either one of them can do this. So I'm gonna write it up here. Right, and again, this is gonna cause the acid to be regenerated, and it's gonna give me my product. So this plus H2 plus water. All right, so the E1 and the SN1 basically follow the same pathway up until you get to the carbocation intermediate. And then from there, that's where the pathways diverge. All right, any questions about that? It's really the same as SN1 until you get to the elimination part. And so let me say a couple more things about this, then we're gonna work two examples that I think will kind of solidify what we know about the E1. First of all, there is no geometry. No, there's no geometric constraint. Remember, for E2, you had to have anti-periplanar geometry. For E1, you don't need that, right? So this can, so there's no geometric constraint. Right? No gem, so it doesn't have to be anti-periplanar. Right? Doesn't have to be anti-periplanar. The other part about the E1 to remember is that you don't need a base. I'm putting that in all caps. If there's a base present, it's not going to be E1, it's going to be E2. If there's a protic solvent present, then it's more than likely going to be E1. And one thing to remember is that this is not clean cut, right? E1 and SN1 compete with one another all the time. So it's not a clean cut like one or the other. Both can happen. Right? Sometimes you may do a SN1 reaction, and depending on the nucleophile that you're using, you may also see a little bit of elimination, right? And depending on for the E1, you may see a little bit of substitution, right? But it has to be, so the question is pretty well defined when we're doing E1, so we'll know what we're doing. All right, so let's go down here to an example. I want to do the hard example last because we only got 5 minutes left. So I want to do this example. Yeah, let's do B. I'm gonna go ahead and snip that. Well, let me get rid of that. Snip that out so we'll have some room to work. And I'm gonna put it down here. right here. So let me paste it in. All right. So this is asking, it's telling us that it's E1, right? Notice the conditions: concentrated sulfuric acid, and then you warm it up, right? So those are classic conditions for elimination, and more importantly, alcohol dehydration. Classic conditions. All right. So look at the product and tell me if that's the product you expect based on where the leaving group is. Because we know the OH is the leaving group. Right, so this is my leaving group. So what's alpha to that? So that's alpha. Is that right? Good. Okay. Thank you. Thank you. Thank you. Who was that?
That was me.
Okay. Thank you. So those are my two alpha spots. All right. So now look at the product, right? This is what the expected product should be, but it's not what we see, right? You expect to see something like this, where you have a double bond here, or you have a double bond here. And you see neither one of those. Right, so let's go through in the last 4 minutes and let's see what happens, or what happened. All right, so we know that I'm not gonna put the arrows in for the first step, just for the sake of time. So we know we're gonna get a hydronium ion intermediate. All right, and then we also know that that's gonna leave. Right, and we know we're gonna get a carbocation right there. So this is the part where the mechanism kind of switches up. Sorry. So this is the part where the mechanism kind of switches up. Right? So if we look at that intermediate right there, and if we look at the product, what it looks like right here is that we took a proton from somewhere else. Right? It looks like we took a proton from right here, because there is a hydrogen here to put our double bond in. Are you following? And so if we did that, so the product tells us that the H plus got removed from that carbon. So if that's the case, then that means that the carbocation had to end up here. All right, so that means that the carbocation is at a different site. So how in the world can we do that? How can we get the carbocation to be, how can we shift it? How can we get the carbocation to go from being here to here? What can we do? You may, or if you didn't pick this up in part 1, then I'll go ahead and show you. All right, so there's a hydrogen here. And sometimes if you have carbocation that's less stable, and it's next door to a carbon that will give you a more stable carbocation, you'll get what we call a hydride shift. Anybody remember that from part 1? Right,
Yes.
it's a type of rearrangement. So the hydrogen, and when I say hydride now, I mean a hydrogen with both electrons, like it's a negatively charged hydrogen. But it doesn't come off, it just moves, right? It's a different type of it's a type of rearrangement. So what happens in this case is this, right? So this bond migrates to here. So that's going to give you a different intermediate. It's going to give you this intermediate where the plus charge is now on this carbon, and then that hydride moved to here. Keep in mind there's already a hydrogen there, so I'm gonna draw that in blue. Right, and now there's still a hydrogen here that either the water or the conjugate base can pull off to get you to the product. I'm gonna use the conjugate base. So that's gonna come here, boom, and then boom, like that. All right. So those types of rearrangements are they can happen if you're doing an E1. It just depends on the type of carbocation intermediate you're working with. I'm gonna write that here. All right, so anytime you see a product, an elimination product that doesn't look like the expected product, then you have to think about some type of rearrangement happening. Right, there's another problem up there that's similar to this one that I want you to work on, and it's let's see. Yeah, it's C right here. But in this case, instead of a hydride shift, you're gonna do what's called a methyl shift. Right, because you can see in the product over here that one of those methyl groups from up here actually migrated. So it's the same mechanism. When you get to the carbocation, instead of doing a hydride shift, you'll do a methyl shift or move the CH3 group. So the reason the hydride shift even happens is because, where am I? And I'm gonna stop after this. All right, here we go. The reason that hydride shift happens is because you went from a secondary carbocation here to a tertiary carbocation here. So it's the reasoning is to make a more stable carbocation. So you went from a secondary to a tertiary. That's why that rearrangement happens. All right, I gotta stop. Let me put the date right here. All right. Any questions about anything?